Hi, I'm Vanessa Gutierrez from IMPLAS, and I'll present the low-energy heating system based on Joule effect, developed in JOSPEL project. First, a glance on the presentation content. We'll review the JOSPEL fact sheet, partners involved, project's objectives, concept design to achieve these objectives, improvements proposed, and finally, we'll present the Joule heating system that are being developed in the project, which include rigid thermoplastic panels and conductive fabrics. JOSPEL project consists on the development and implementation of low-energy passenger comfort system based on Joule and Peltier effects. It lasts from May 2015 to October 2018. It is founded by a European called Horizon 2020, optimizing systematic energy management in electric vehicles, with a budget of over 6.6 million euros. The consortium is composed by 14 partners from 9 different countries, which are IMPLAS from Spain, Alke from Italy, Fraunhofer from Germany, Atos from Spain, Klinkar from Luxembourg, Simoldes from Portugal, DOK-ING from Croatia, CITAC from Spain, Insero from Denmark, Thermoplastic from Spain, Arkema from France, Sidete from Spain, A&B Design from Italy, and European Thermodynamics from UK. In this pair diagram, we can see the overall participation of each partner in the development of the heating and cooling systems. On the heating system, we can find Thermoplastic, IMPLAS, and CITAC. On the cooling system, Sidete, ETL, and CITAC. On the acrylic glazing, Arkema and IMPLAS. On the battery management system, Klinkar, Sidete, and Fraunhofer. Cabin and glove box insulation, A&B, Simoldes, Alke, DOK-ING, and CITAC. And on the energy efficiency and eco-driving, Atos, CITAC, and Alke. All of these systems will be implemented in electric vehicles manufactured by DOK-ING and Alke, and the data management platform is developed by Atos. The main objective of JOSPEL project is the reduction of at least 50% of energy used for passenger comfort and at least 30% for component cooling in extreme conditions, all with reference to electric vehicles current on the market. To achieve this objective, the following concept was designed: the development of a novel energy-efficient cooling system based on Peltier cell technology, the development of a novel energy-efficient heating system based on Joule effect, improvement of vehicle insulation, improved energy recovery from heat zones and increased battery life, and innovative and eco-driving strategies and electronic control of power flows. Related to this concept, we know that for increasing distance range of an electric vehicle, there are 4 main actions that can be implemented: increase engine efficiency, reduce car weight, improve battery efficiency, and improve energy consumption. These last 2 actions are part of JOSPEL concept. The expected improvements to achieve in the project are an energy reduction of 30% for the heating system based on Joule effect, 25% on the cooling system based on Peltier effect, 15% on the battery consumption due to optimal thermal management, 12% on the thermal management of other electrical vehicle components and eco-driving technology, and a 3% of weight reduction and better insulation of the cabin. Now going into matter. One of the systems developed in JOSPEL project are Joule effect-based materials. But the Joule effect is the process which the passage of an electric current through a conductor releases heat. The main objective of this task is the development of a novel and innovative heating system based on the use of Joule effect in thermoplastic sheet and thermoset coating. Also, the reduction of energy consumption of at least 30% in comparison with current PTC heaters. These objectives will be verified by a maximum power install of 800 watts or less. So based on Joule effect, two systems are being developed. A rigid multi-layer sheet in a thermoplastic matrix, which is completely recyclable and is produced by a fast and cheap process, and fabrics with heating coating in thermoset resin, which is very flexible and offers a higher heating capacity. Regarding the heating panels or the thermoplastic conductive panels, the conductive particles are dispersed in a thermoplastic polymer matrix by means of a compounding process. This compound is then used to produce the panels via gas extrusion process. The panels can be reprocessed again in the same or an alternative product. Furthermore, the temperature of the panels can be controlled in function of the power supply, as can be seen in this graphic. Here is an example of a thermoplastic sheet heating process. It is an accelerated video. In this video, we can see the evolution of the temperature from 30 to 80 degrees Celsius in 2 minutes. We also can see that the heating process is very uniform all across the sheet. To sum up, the main advantages of these fabrics or these sheets are the uniform heating and efficient, as the aim is to warm the passenger instead of heating up the air inside the vehicle, the lightweight, their recyclability, and the customized heating performance, varying plastic formulation and panel geometry. An example of the latter can be seen in these two graphics, where just a change in the dimension can affect the heating capacity. The main application of the rigid panels are part of the car in direct contact with passengers or very near the passengers, such as door panels, seats, and plastic mats. Regarding the heating fabrics, we have found that the use of electrically conductive nanoparticles offers improved electrical properties. In this case, nanoparticles are transferred to the fabric through a coating process by means of a colloidal dispersion specially designed for this purpose. The main performance of the fabrics are a voltage range between 5 and 220 volts, AC or DC, a power range up to 2000 watts per square meters, temperature range up to 100 degrees Celsius, and a temperature increase of around 50 degrees in less than 1 minute. The main properties of these fabrics are they uniformly heat large areas, they are lightweight, they have flexible electrodes, keeping electrical and structural stability. They're completely customizable, heating performances fine-tuned through specific formulations of the conductive dispersion. An example of the fabric heating behavior is the following. Applying 24 volts at 30 watts, we can obtain heating to 60 degrees in 60 seconds and up to 70 degrees in 3 minutes. The main applications of the conductive fabrics can include the steering wheel cover, car seat, rubber mat floor, car arm rest, laminate flooring, or mat floor. To summarize, in JOSPEL project is being developed a novel and innovative heating system based on the use of Joule effect in thermoplastic, obtaining sheet and thermoset coatings. We have achieved an important reduction on the energy consumption of heating and ventilation and air conditioning systems. Currently, final prototypes are being produced and the integration of all systems is being done. And furthermore, these systems are being validated in a broad range of weather conditions, including evaluation of real users. For any information regarding the project, you can contact us directly or through the project's email. Thank you very much for your attention.